Hello, everybody. My name is Alton McCarthy, and I am one of the members of the IEEE RFID 2020 Organising Committee. Today, I am fortunate enough to have stolen some time from Megan Brewster, who is VP of Advanced Technologies with Impinj. Now, Megan has very kindly offered us some of her time, and I want to talk to her briefly around the area of RFID, needs in the industry and future major trends. So Megan is going to talk to us about some of the areas that Impinj are focusing their technologies and their time on at present, which gives us an idea of where the market is potentially going. So Megan, first and foremost, thank you for joining us today and for allowing us to steal so much of your time.
Thank you, Alton, for having us. We really appreciate everything that IEEE does for our industry.
As do we. We're so appreciative of you guys. Megan, I'm going to start straight into some of the questions if you don't mind. We're going to talk a little bit about Lossy Dielectrics. And I want to ask you, why are they so important to industries wanting to use RAIN RFID?
Yeah, thank you, Alton. So in RAIN RFID, in our industry, we want to tag everyday items. And sometimes those items are made from materials that will actually degrade the performance of the RAIN RFID system. And one example of that is a material class that we refer to as Lossy Dielectrics. So Lossy dielectrics are materials that inhibit RF signals from performing efficiently as intended. So let me give you two examples of those in the real world. The first is perishable food items like fresh leafy green lettuce, which we'd like to tag so that we can ensure food safety by tracing and tracking these perishable items through the food chain and ensure that the food you eat every day is safe for consumption. Consumer packaged goods are also a part of perishable food items. So that could look like a carton of fresh orange juice. And there are literally tens of trillions of food items every year that could benefit from RAIN RFID. In addition to food safety, tagging food items with RAIN tags can also help reduce food waste, can enable omni-channel sales, and connect consumers with more information about the food items that they're eating every day. One particularly exciting food initiative is by the Japanese government, which is aiming to tag all of the food items within their 55,000 convenience stores by 2025. The second lossy dielectric that I want to highlight today is the human body. There are many applications where the tag is near human bodies. For example, if we want to time marathon runners, then in this case, the tags are placed in the race bibs that they wear on their shirts. So those tags are very close to the human body. Another example is hospitals that want to ensure that their patients are receiving the best care. And they do that by giving those patients a RAIN RFID enabled wristband. Lossy dielectrics are challenging to tag because they degrade the system performance by two things. First, they detune the tag antennas, and then second, they absorb the incident RF signal that's coming from the reader.
Very interesting. So they do present a tremendous challenge to RFID and its functioning from what I'm gathering from you, Megan. Can I ask maybe for a little bit more detail there, if you don't mind, please? In specific, how do dielectrics actually detune RAIN RFID systems?
Of course. So materials of all types can influence the performance of wireless systems like RAIN in four main ways. So the first is shadowing. They can block or obscure the path, the RF signal between the reader and the tag. They can reflect that signal, which could lead to multiple paths that the RF signal can take as it moves from the reader to the tag and back to the reader again. There are changes and antenna radiation patterns, and that can make the pattern weaker or stronger in particular directions. And materials can also detune antennas, and that's particularly important for lossy dielectrics. In this case, it changes the antenna impedance and then hence the impedance matching between that antenna and the chip that's on the tag. So a lossy dielectric impacts these last two items. It reduces the strength of the antenna radiation pattern through absorption, and it detunes the tag antennas. So let's dig in a little bit more to how dielectric materials do this. So think back to the two examples of the lossy dielectrics I gave you earlier, a head of leafy green lettuce and the human body. So both of these materials have high dielectric permittivity and relatively high conductivity. So what do I mean by that? High permittivity means that the material polarizes easily in the presence of an incident RF wave. So in the case of lettuce and the human body, both of these items have high water content. Water is a polar molecule, so it will respond to an incident field more strongly than, say, a nonpolar molecule or a molecule that may be constrained within a solid crystalline lattice. This causes the optimal frequency of performance for the tag to shift down to a lower frequency, and we refer to that as tag detuning. Another key metric for Lossy Dielectrics is the dielectric loss tangent, and this denotes the dissipation factor. The bigger the loss tangent, the bigger the energy loss that comes with the detuning frequency shift. And this is bad for antenna gain. High conductivity, so just digging in a little bit more there, that means that the electrons and other charged particles can move very easily through that material. And these vibrations lead to additional energy loss within that dielectric material. And this reduces the efficiency of the tag even further. So both of these factors result in a loss of the overall electric field strength.
Wow, my goodness, there's quite a lot to take in there. There's actually a lot of factors that you must consider in tag design and in terms of the design of the overall system from tags to readers. So moving on to the actual system, Megan, with everything that you've presented to us so far in terms of the products and in terms of all the factors that can possibly impact on system performance, what is the impact, the overall impact to system performance?
So to understand the impact of Lossy Dielectrics on the overall performance of the RAIN RFID system, let's think about the RF link budget. So this is the budget of RF power that we spend as the RF signal travels from the reader to the tag, is backscattered by the tag, and then travels from the tag back to the reader. When a tag is attached to a lossy dielectric, that link budget is degraded because the tag's antenna is detuned and the incident RF signal is absorbed by that lossy dielectric. So because of this, two bad things happen with regards to system performance. The first is that the tag now needs more power in order to wake up. So that means greater power on tag forward, or POTF. This effectively reduces the range over which the tag can be read. It's also important to note that if the tag doesn't turn on, the entire RAIN RFID system fails. The second bad thing is that more power is absorbed by both the detuned tag and the dielectric to which it's attached. So now the signal reaching the reader is weaker, and that makes it harder for the reader to process, which can be especially difficult for handheld readers. So this means that the RAIN RFID system overall needs more RF power in order to maintain the same level of performance.
Very good, very good. That is a tremendous amount of detail. Thanks so much for that. So from a practical perspective, Megan, clever people like you guys at Impinj, how do you work around all these challenges to make RFID a ready technology for industry today? What are the workarounds for these challenges?
Yeah, this is an industry-wide problem, and Impinj is just one part of the solution. And our partners that are manufacturing inlays and providing tags or setting up these systems at their on-site deployment location, we're all playing a part in maximizing system performance when we're tagging these lossy dielectrics. But in terms of breaking down the system components and what we can do to work around these challenges, let's start with the tag, which is comprised of the chip, the antenna, and the inlay. So most RFID inlays on the market right now are designed for retail applications. So this is where the loading from any dielectric is relatively low. In these cases, your standard T-match dipole antennas that you see on the market work fine. And in general, these inlays are not designed to work well near lossy dielectrics. So a natural question is, how might we design a RAIN RFID tag for use near lossy dielectrics? So starting with the chip, which is the brain of the RAIN tag, one approach is to make that chip more sensitive. And in Impinj, we're very proud of the work that we've done over the last 2 decades to drive chip sensitivity to historic levels. So we started in 2000 with the Monza 1A chip. It had a sensitivity of -9 dBm. And today's new M700 chip is at nearly -22 dBm. So this means that we've increased the read range 5 times, from almost 6 meters with the Monza 1A to over 25 meters with that new M700 chip. This increased chip sensitivity gives tag designers more options. They can use the same antenna and reap that increased read range, or they can hold the read range and the performance constant and spend some of that RF link budget in other places. For example, by tagging Lossy Dielectrics that will absorb some of that RF signal. They could also shrink the inlay size. A second option is to build an auto-tune circuit on the chip that would shift the impedance of the tag to match that of the antenna when it is detuned. But the challenge here is that auto-tuning requires capacitors. Those capacitors take up precious real estate on the chip, and that increases the overall size of the chip and thus the cost of those chips. Because Lossy Dielectrics detune antennas so significantly, the amount of capacitance that you'd need to add to the chip in order to offset that very large detuning would take up a good amount of space. And obviously a goal with RAIN RFID is cheap tags so that we can tag everything. So that would be kind of going in the opposite direction. The next component in the tag to consider is the antenna. And so there's a few approaches that we've seen from our partners and from academic literature for designing a tag antenna for a Lossy dielectric. So the first is that you could design a special antenna that works optimally for lossy materials, but then that same antenna may not work well when it's attached to materials that are not lossy. The second option is to use patch antennas, where you've got a ground plane that shields the antenna from the Lossy dielectric that detunes it. The challenge here is that then you've got 2 layers to the antenna, which increases the cost of the tag. And the tag can end up being rigid or thick, which can be uncomfortable if you've got a wearable application, again, where that tag is near a human body. Also, patch antennas work over very narrow band. And so that means it'll be difficult to design an antenna that works for the various bands of frequency bands of multiple geographies around the world. A third approach that we've seen is to have a tag with an array of antennas. This does come with a higher price tag and a longer design cycle time for that tag. So now let's consider the tag overall. So here we've seen 3 main approaches to designing tags that work well with Lossy dielectrics. The first is to put a spacer between the tag and the dielectric that detunes it. And these are usually foam tapes that are on the order of about 5 millimeters thick. The thicker the spacer, the better performance, but that also means a bulkier tag. The second option is to make a really big tag. Bigger antenna means that the inlay can work with weaker RF signals. If the tag's going to get wet, such as if you're timing a swimmer in a swimming race, remember water is a Lossy dielectric, you could encapsulate the tag. That's the third approach. So separate from RAIN RFID tags, which are by definition a passive technology, you could also design a battery-assisted tag to increase the read range. Of course, the cost of the battery will increase the overall cost of the tag. So we've talked a lot about tags, but what about the rest of the RAIN RFID system? So with the reader, you want to think about the zone in which the tag is read. So if the tag is near the reader, on the order of centimeters away, then we can work with the near field. The magnetic coupling that's active in this transitional near field region doesn't change the presence of Lossy dielectrics, or doesn't change in the presence of Lossy dielectrics, but you will lose that benefit of far field, which is that wide range coverage. We can also position the reader to avoid shadowing by the Lossy dielectric. You could also look to use a linearly polarized antenna to increase the power incident on the tag. So as you can see, there are many different ways that we can improve the RAIN RFID system performance when we're tagging Lossy dielectrics, from the individual components of the RAIN RFID tag to thinking about the entire system, which includes the reader. And it's critical that we investigate all of these approaches as we look towards exciting new markets like the food industry.
Megan, thank you so much for all that information regarding RFID, the systems, and some of the ways to improve it. I'm sure it'll be very heartening for people after they listen to your talk. For people who are getting into RFID, because this conference, we have a lot of academics and we have a lot of researchers at different career stages. So while they may understand one particular area of RFID, the bigger world around RFID may be very much unknown to them. But to get into some of the specifics, some of the areas that you've spoken about there, is there any other places or good sources of information you could recommend?
Yeah, of course. There's a lot to learn on this topic, and the RAIN RFID industry has already made quite a bit of progress. So you can look at commercially available tags from our partners that are manufacturing tags and inlays, and they'll have a number of specialty tags designed for use on Lossy Dielectrics. There's also a ton of great academic research on this topic, including from IEEE members. So we've got a few references that we can point folks to related to some of the approaches that I described in this talk.
Megan, that sounds super. Thank you so much for taking your time, and I promise we won't take any more of your time. Megan Brewster, thank you very, very much for giving us a whistle-stop tour of Impinj and all the great stuff that you guys are doing, and I really hope you continue that way.
Great. Thank you, Wilton.